Good morning, everybody, and welcome to another spring showcase. It's great to see you all here today, and thank you so much for taking the time out of your day to join us today. Alongside Anglian Water, who will be taking us on a journey through their Ofwat-funded All-Streams HTO project and how it aims to transform how the sector approaches sludge treatment and their circular economy goals. For those who aren't familiar with Spring, we are the Centre of Excellence for Innovation in the UK and Ireland, and our main objective is to enable effective delivery of innovation and collaboration by creating centralised intelligence for both water companies and suppliers. Our mission is to attract, connect and support innovators across the industry to accelerate transformation. And that's why we facilitate and host knowledge transfer events such as today too. Through knowledge sharing, Spring supports the transfer of learnings from an innovation project to the wider sector, creating project legacy that helps innovators to identify and adopt the right solutions at a greater pace. Last year, we actually partnered with Ofwat, the economic regulator for England and Wales, to build out a view of what best practice knowledge sharing actually looks like. So we brought together senior leaders and innovation managers from the water companies to design a vision for knowledge sharing and what it is that we're trying to achieve. And we came up with these kind of 6 best practice principles for knowledge sharing to achieve world-class knowledge sharing culture for the sector. I'll quickly whiz through those now. So number 1 is to learn from what already exists before committing to innovation projects. And to aid this, we did create the Spring platform, which hosts a multitude of case studies and aligned to the priorities laid out in the Water Innovation Strategy 2050. Number 2 is target innovation insights to the right audience to meet our objectives. So for example, today, do we have the relevant people on this call who can take action on the knowledge shared today and within their own organisations? Number 3 is that insights are regularly shared through multiple channels from day 1 of the project. So historically, when we have knowledge shared in the industry, it's been towards the end of a project, and we want to make sure we move towards a model where we're sharing from day 1. Number 4 is that sector knowledge is open and centralised. And number 5 is that insights from both innovation successes and failures are shared. So as we all know, the lessons learned from failures and challenges are just as important as the lessons of success. And we'll hopefully hear about a mixture of both of those from our presenters today. And number 6, finally, is people are empowered to receive and embed lessons from external sources. So Spring and the presenters on this call can all share the knowledge today, but we want to make sure that the receivers of the knowledge actually have the capacity and the resources required to make that change, and that you feel empowered to do so. So back to today, I'd just like to give a warm welcome to the audience members joining us live. We are joined by the UK and Ireland water companies, supply chain, academia, and plenty of overseas colleagues too. So welcome to the call, and thank you so much for joining us. As always, we will include a poll at the end of the event to gain your thoughts. And answering this poll is the most impactful way you can help make sure that these events are providing value to you, your organisation and the wider sector, and that these showcases are in fact supporting faster-paced adoption of solutions. We'll launch that at the break, so please do make sure to submit your answers when that comes through, and we'll also launch it at the end for those who didn't get a chance to submit in the break. You'll also get the chance to ask questions today to the project team, so do make sure to keep putting your queries in the chat throughout today's presentation. So I'll just quickly run through the agenda and introduce our speakers before we kick the session off. So we'll be starting off with a strategic introduction from Anglian Water, followed by a technical overview from Cetogenics, and then we go a little bit into the concept to realisation piece of All Streams HTO, the experimental work that's been done, how we're actually deploying HTO in the water sector. We'll have a quick break, and then we'll come back for a deep dive into the lessons learned and the questions and answers. So like I say, do make sure to keep putting your questions in the chat throughout today. We'll hear from Will Davis, Circular Economy Delivery Manager at Anglian Water, David Inman, Innovation Projects Manager at Anglian Water, Trevor Stuttridge, Chief Executive at Cetogenics, Daniel Gapes, Chief Technical Officer at Cetogenics, Celeste Gritty, postdoctoral researcher at Cranfield University, Stephen Stewart, MSc student at Cranfield University, and Ben McMahony, principal resources process specialist from Atkins Realis. Must apologise, I don't know what's happened to the job titles there, they've come a little bit out of sync. But without further ado, I'll hand over to you, Will.
Super, thank you, Leah, and thank you everyone for joining this morning. Yeah, I'm Will Davis. I'm Economy Delivery Manager, or lead, as role changes happen here at Anglian Water. And I'm just going to give a bit of a quick context into how Anglian Water are viewing these challenges and why it's so important that we work on things like HTO and share that with the wider industry. So I'll just now get us forward. And up here on the left, you can just see this infographic, something produced by Stockholm Resilience Centre, which pulls out the different planetary boundaries and some work they did to see where our current global society operates outside a safe space. I'd like to draw particular attention to novel entities. On the top there, you can see that's by far the largest outside the boundary. And novel entities basically just means any chemicals that are entering the environment from man-made sources, so non-natural chemicals. And again, you can also see biogeochemical flows there on the bottom, phosphorus, nitrogen, and of course climate change is in there as well. And the reason I pulled those out is that particularly they're very relevant for the water industry. We know we're having increased demand on limited resources. We're seeing increasing amounts of chemicals coming into our works from emerging substances, such as PFAS, and with things like phosphorus, nitrogen, with limits being imposed through the Environment Act and other regulation, we're seeing an increased need to strip those back out of the environment. But as a common sort of myth of the water industry, we don't really treat wastewater. We actually just move those chemicals out to ensure that the environment isn't affected, but they have to go somewhere. And hopefully what we'll see today is one method in which we can meet some of these challenges. And I've just pulled out here as well that, this isn't just a water sector challenge. I've pulled out the water sector bioresource strategy there, but the UK government's also very involved in this space around net zero and the current Circular Economy Task Force, which is due to release their initial report later this year. Particularly for the water sector with the bioresources strategy, what we've seen over the last few years is an increasing amount of regulatory change, which is reducing our ability to use traditional route of sending biosolids to agriculture, with things like PFAS emerging and other emerging substances where we aren't quite sure what the impact on the environment is. That rate of change may pick up. And as the UK is currently reliant on a single route for disposal or recycling through to land, we know we need to find something different. And again, today is a great example, something we could do with that in collaboration. And again, today is all about circular economy, so I just thought I'd pull up a slide detailing what that is. And traditionally, we've worked in a linear economy in the UK, and in large aspects we still do. But circular economy is not a new principle. It's been around since the 1970s, but we've seen real traction over the last few years. And as the water sector is inherently reliant on a circular system through the water cycle, it makes absolute sense to try and align our operations as much as we can to a circular economy so that we don't damage the environment and can act as good custodians of it. So really the ask for today is just to recognise that although there are lots of really excellent technologies out there being trialled, and I think this is one of them and really promising, that there's no single approach that's going to be a panacea to all of the issues that the industry is facing around biosolids and others. There are multiple ATC techniques in trial, advanced thermal conversion, and to ensure that as we move through this next 5-10 years where we're going to see significant changes in the space, we all need to be working together to make that happen. And there will be learnings and trials we can get from all different sources, from other water companies through to NGOs, through to third parties, through to our regulators, of course. And the holistic pooling of knowledge is really crucial to that, and it's quite an important tenet of a circular economy, actually, that we don't just look within our lane. So just as a clarion call, please do ask any questions you have. Please get in touch with us, and also please share your feedback from today. And finally, we just got our values there on the bottom, and again, it just reflects, I think, the absolute need for what we need for these sorts of projects and these sort of transitions we're going to see in the industry. We must do the right thing. We have to build trust, and we have to always be exploring. And as you've all joined here today, we're all certainly hitting that last one. So without further ado, I'll hand over to Cetogenics.
Good morning, everyone. Thanks very much for the opportunity to take you through the cetogenics journey and the technology we've developed. Joined today by my Chief Science Officer. I'm the CEO and co-founder with Daniel and two others of cetogenics, built off IP that we developed over a number of years, and we'll take you through that. So we touched briefly on this. There are many choices in advanced thermal conversion, but they do sort of categorize between sort of four broad matrix areas. There are dry processes where the waste material needs to be dry, such as pyrolysis and incineration or gasification. And then the wet processes, essentially the hydrothermal type processes or the supercritical processes. And then they've subdivided into non-oxidative, so processes that don't require oxygen or cannot use oxygen for reasons of the chemistry and the engineering. And then there are others that benefit from oxygen, such as hydrothermal oxidation, which is the technology we'll talk about today. And hydrothermal oxidation, as we'll describe in a moment, occupies a unique space in this matrix, and we feel offers some very compelling opportunities for the sector. And this is partly why. Hydrothermal oxidation has relatively low temperatures and pressures, so typically 240 degrees Celsius, maybe 90 bar of atmosphere pressure. And these lower temperatures and pressures means capital costs are relatively low. It also means that we're able to operate a fairly broad window or envelope for production of the value-added materials that we're looking to get out of the process. And it also means we can operate under autothermal conditions, which means we can recover heat from the system to power the system, so we don't use excessive amounts of electrical energy. And for these reasons, we think there's a real advantage to hydrothermal oxidation within the bounds of advanced thermal conversion systems. And this is why we like it. Hydrothermal oxidation really lends itself to deconstruction rather than destruction. So we're able to break the materials down, but still retain molecular value from the waste material that can be recovered and repurposed. The products from our system, such as ammonia, phosphate, and biomethane, have existing supply chains, so we're not having to create new value chains or supply chains. All of the products that come out of hydrothermal oxidation typically are defined as low carbon, so they benefit from a greenhouse gas perspective. Our systems are autothermal, so we return 5 to 10 times the energy out relative to the electricity energy that we put in. And because of the low capital costs and operating costs, particularly around electrical energy, our TOTEX, or combined CapEx and OpEx, is about 50% lower than the other advanced thermal conversion systems. And finally, with respect to efficiency, we have no secondary outputs. So, for example, hydrothermal oxidation doesn't generate biochar, and therefore it doesn't have to have another market for secondary products. It's this interest and excitement around hydrothermal oxidation that led Cetogenics to create CetoBoost and to create the IP around CetoBoost. In simple terms, we're taking heat, temperature, and air, and we're deconstructing the waste material into renewable energy, nutrients, and other biomaterials. And this is technology that we've been developing over a number of years, and I'll ask Daniel now to take us through some of the details.
Right, thanks, Trevor. So just drilling in, as Trevor said, a little bit more into what is hydrothermal oxidation. And so if you could imagine for a moment a pressure cooker or a pressure vessel, so represented as the large box that says CetoBoost on this slide. And into that pressure vessel, we would feed organic waste that is wet. So wet waste, and it may come from the agricultural sector or industrial sectors or the municipal sector, which is the point of focus for much of our work at the moment. So wastewater treatment sludges. And they would come into this pressure vessel at about 6% dry content. So come in as a sludge or a slurry. And with those wastes, we add an oxidant. So we add oxygen into that system, and it's pressurized up to about 240 degrees C and is maintained under pressure. And the pressure in the system ensures that while the temperature is above 100 degrees C, the water does not boil. So all the reactions that occur within hydrothermal oxidation are happening in the liquid phase. What happens when you create that environment is you get what could be termed a wet combustion. So just as you might burn a piece of paper in a fire, the organic material gets oxidized but in the water phase and turns into carbon dioxide and water, and heat is generated. And we use that heat to maintain the temperature of the system. So no external heat is required to be retained at 240 degrees operating temperatures. Not all of the organics are burnt to CO2 in hydrothermal oxidation, and which is what we want. What we want is to convert that organic material, as much of it as we can, into fermentable organic carbon, which is in the soluble phase or in the water phase. And along with that, the second product that gets formed is from the proteinaceous materials that enter in with the waste. Ammonia is formed. And the third piece of the product pie that we generate is the phosphorus, which comes in with all of these wastes, is retained in the inorganic fraction, which comes out within the ash that's generated from the oxidative reactions. And so we have here examples of generation of three product types. One, which is the dissolved organic carbon, which can be taken on and generate renewable energy, as we'll talk a little bit about subsequently. Renewable chemicals in the form of ammoniac or nitrogen, and nutrients in the form of a phosphate product. Next slide, thanks. And so what actually does it look like? And so on the left-hand part of this slide, we see biosolids, so a wet organic material that goes in and is transformed to what you see an example of on the right-hand side bottle, which looks like water, and that's in fact what it looks like. You're generating a watery product, and at the bottom of that bottle, you'll see a thin layer of inorganic material, which is where the phosphorus-containing ash is retained. Thank you. And how well does HTO do its job? And so what the first thing that it does is it's excellent at destroying the particulate fraction of the organics. And so as represented by volatile suspended solids measurement, you get 90+% destruction of the suspended solid material. The product that's formed gives you an opportunity to take and go on to subsequent biological processing to generate methane. And so there's opportunity to enhance the methane production of a given site. There is a significant amount of decarbonisation which is associated with what we do. Generation of nutrients, so the ammoniac or nitrogen is recovered to greater than 75%, and phosphorus, we can recover up to 90% of the phosphorus that comes in with the incoming material. And there are some really interesting opportunities around substances of concern, including microplastics, and HTO is particularly good at eliminating many of these microplastic contaminants. And so how might this fit in the context of a wastewater treatment plant? And so if you represented here is what happens to wastewater treatment sludges as they come into a sludge treatment works, and they undergo anaerobic digestion with the production of a biogas where energy is generated. And a digestate is formed, and that's thickened, and the thickened sludge in the context of many wastewater treatment plants is taken to land, and the centrate from the thickening is returned to the wastewater treatment plant. And what cetogenics technology, CetoBoost does, or hydrothermal, to integrate that into the plant, you completely eliminate the digestate to land and take that through the digestate through the hydrothermal oxidation subsequent to that, a solid separation stage where the ash is removed, recovering the phosphate. Ammonia can be stripped from the processed liquor to create a ammoniacal product, and the liquor can move on to various fermentation options. For example, putting back into the anaerobic digestion or standalone production of biogas, and there are other opportunities for that, including generation of biopolymers and other low carbon chemicals. The final process waters from that can be safely returned to the wastewater treatment plant.
So Cetogenics has been operating since 2022, but it builds on a 20-year journey of the co-founders, including Daniel and myself. We've been working extensively in the waste to value space, and particularly focusing on hydrothermal oxidation as a platform technology. So that work historically done through our associations with government agencies in New Zealand and universities has developed the underpinning IP, the underpinning R&D. We've completed proof of concepts many times in the laboratory with many waste streams, including biosolids from different wastewater treatment systems. And during that period, we also took the technology through to a first generation TRL4 system, which was essentially a batch system. And since our formation in 2022, we've built our team up in New Zealand to a team of 12, and we've taken the technology through 2 iterations. The first one was basically a proof of concept beyond batch to be continuous, and the 3rd generation plant we've just recently commissioned and have been operating has integrated some novel IP into the reactor design, and is also now starting to process commercial products at a scale of around 50 litres an hour, which is about 1/60th of the final scale that we'll be targeting for the future. And so this is our target concept. So far, looking at modularity as a feature so that we can plug and play into the sites and have low land requirements for the system, looking to be low disruption, so we don't need to modify the AD, etc., in order to position the system in place. The module would be 25,000 tonnes a year, what we call our CB3000. We have aspirations to take it to 40,000 tonnes per year for certain scales, which I'll talk about in a moment. And if necessary, if we're looking at very large sites with large amounts of biosolids or other waste, then it can be done in a non-containerized model where it can be bespoke and go to large scales. Because we've been working on the technology for over 20 years and we've had lots of experience with it, we are quite confident in scaling. It's really just a case of more scale rather than changing a lot of the general principles. It's just putting more through the system at higher flows and higher reactions. So for this reason, we think modularity enables scale into the UK water sector. So if you look at the range of UK sludge treatment centres around the country, then you look at the different sites cumulatively, then our 25,000 tonne a year system would serve probably the first 100 scaled sites in terms of the size of the sites and the amount of material they process. Then we could start to use our 40,000 tonne a year sites for the next sort of tranche, next 100 or so of those sites. And then there are those few very large sites in the UK which have large amounts of solids, and that's where we would consider looking at the bespoke system. So we're excited to be part of this initiative with the UK water sector. We're excited that our technology, which has been in development for some time and has the opportunity to be introduced into the water sector, eliminates land disposal, as Daniel indicated, because we eliminate organic waste itself as a sludge, allows us to optimise the wastewater treatment plant flow sheet with respect to nutrient recovery and energy recovery, encourages and meets the needs of waste circularity, and then generates energy resilience for externals in terms of the form of enhanced biomethane production. And that's why we're keen to be working with you all to build renewable futures with no waste left behind. And with that, I'll pass it on to David.
Thanks, Trevor. So good morning, everyone. My name's David Inman. I'm Innovation Projects Manager at Anglian Water. So I'm going to talk a bit about the concept to realization about the All Streams HTO project. So in around August 2023, We began speaking with Cranfield University, myself, Bruce Jefferson, Ewan McAdam. We have a close collaboration with Cranfield over the years. So we were talking and I suppose sort of brainstorming around the subject of sludge to land and the challenges that the industry has in terms of the risk of that outlet closing down, and what are the alternatives? What could we do as an industry? And the conversation centered around maintaining or improving the value that we can get out of bioresources to land. So that was kind of the remit that we had as a sort of when we were brainstorming, and we went through the different advanced thermal conversion processes and looked at the pros and cons and some of the challenges, risks. And we came to our conclusion that hydrothermal oxidation looks to be a very good route to enable recovery of resources from biosolids, which is really important at the moment. In the UK, most sludge is most bioresources go to land. They're valued in terms of their phosphorus content and their soil conditioning properties. So we really wanted to maintain or improve that aspect, but also perhaps managing the substances of concern is probably the priority at the moment that we're looking at as an industry and the driver. So that's where the project came from, and then we connected with Cetogenics, Trevor, Daniel, Rob, and the team there, and we started putting together a scope for a project. And now, in addition, we'd also been working with Cranfield over the last 5 years on vacuum ammonia stripping, which is a novel approach, a low energy approach to ammonia recovery, really exciting, and it also produces a product that is of a better quality in terms of concentration and in terms of trace elements that are in there. So we connected these two projects together and recognized we had a really strong system for resource recovery from bioresources that could improve the current situation. So we're funded in April 2024. We received the great news that the project had been awarded funding, 1.53 million. The project would proceed over 21 months. So from September 2024, we'll be looking to finish next year in June. And the idea was a pilot scale hydrothermal oxidation unit and these downstream refinery processes, which are really central to the project. We had a plan and designed, built and operated at Cranfield, to be designed, built and operated at Cranfield University. And then also looking at one of our Anglian Water's largest sludge treatment centres in Milton Keynes, Cotton Valley, to actually do the designs around a full scale, how we could integrate HTO and those downstream recovery processes at Cotton Valley, and ultimately to look at what the value proposition is, to put some numbers against the cost of recovery, the value, the revenues from that, carbon and energy, and how that would fit into the flow sheet. So really, this is a simple process flow diagram that shows HTO and downstream recovery. This is our sort of our aim to demonstrate that we put digested sludge directly into HTO, and then we look to recover the phosphorus ash. We look to also recover ammonia as a sustainable source of ammonia, and then also convert the organics into biogas. And then the remaining liquor from those processes would be of a suitable quality to go back to the head of the works. Now, an additional aspect to this is that when we put digestate at about 6% by dry solids from a digester directly into HTO, that removes the need for any dewatering. So we are not producing any liquors from that process. It also means we're not having to dry the sludge, which other ATC processes need to do. So we avoid the high energy from drying, but we also remove high strength ammonia returns going back to the mainstream, and we know already that they cause process emissions, nitrous oxide emissions on secondary processes, and we've estimated that we can reduce those by removing that step by around 30%, so a 30% reduction in nitrous oxide emissions. So that's a really major advantage as well of the approach that we're looking at. So the aim early on in the project was to start to understand what the resource recovery potential was from HTO. And so Anglian Water, myself, our supply chain team, in collaboration with the rest of the team and others in the industry, we completed a horizon scan of possible resource recovery pathways for these products. So in terms of phosphorus, in terms of ammonia, and in terms of carbon. And the idea here was to understand that value proposition. What are the potential revenues from phosphorus? So we were looking at recovering the phosphorus for fertilizer production, from chemical processing, possibly as an aggregate as well for cement production. For the ammonia, again, looking at those different pathways, so using ammonia as a fertilizer, as a chemical, also for energy, either through a CHP or as a hydrogen storage, and also in terms of the carbon, methane production, utilizing as a source for simultaneous nitrification, denitrification in the mainstream process, and also there's CO2 gas that we can recover from that. So they were the pathways that, as a project, we've highlighted as being the most feasible, the highest value, and the lowest risk. So you can see on the right hand side, we've categorized those, and they'll be explored. This is an example of how they'll be evaluated through the project, how we are evaluating those. This is just one example. So working with potential off-takers in the fertilizer and chemical industry, understanding what the purchase price might be for those, and then looking at the value for each of those. So in this case, we're looking at an aqueous ammonia product. For the ammonia, we're looking at methane and then producing phosphoric acid. And what that provides us with, once we have those unit values, we can understand per ton of dry solids what the value is for each of those. And we can see for this example that the ammonia, it has a high value. And then also looking at the carbon impacts of recovering those. So this is an example for now, but as an output of the project, to understand that value proposition, we do need to understand these revenue streams and what the risks are. So the HTO All Streams HTO project is a system development. We're looking at hydrothermal oxidation, but we're looking at those downstream processes, their robustness, their compatibility, and their reliability and scalability. So all of these technology development criteria, we included these. We did a study with a company called Expedition, and looked at where we were in 2024, where we're looking to be by 2026. And you can see down there on the left, there are a number of criteria. It's quite small, but what what I thought would be helpful would be just to do a bit of a dive into 4 of those that we're looking at. So in terms of technology readiness, we're looking to move the whole system. So that's the HTO through to ammonia stripping from TRL6 through to TRL5, sorry, through to TRL6. In terms of integration readiness, so we have already modelled and doing further simulation modelling to understand the best configuration for HTO and downstream processes at Cotton Valley. And then system readiness, we're looking to validate an optimized flow sheet through testing at pilot scale at Cranfield, and that will provide confidence for scaling up to know that those processes are compatible and that we can operate them in a stable way over a number of months. And then market readiness, this is vital for the resource recovery. So we want to understand what levels of quality control we can achieve. Can we get that constant quality control of the recovered products? And we've been doing that by consulting with potential end users in the fertilizer and chemical processing industries. So that's an overview. It's been so far it's been a lot of progress, a lot of learning. The next few months we are continuing the experimental work. We've been now operating the pilot plant for nearly 2 months, and I'm going to hand over now to the Cranfield team, who will present some of the early results that we've seen. So I'll hand over to Stephen Stewart from Cranfield. Thank you.
Hey everyone, I'm Stephen. I'm a Masters of Research student at Cranfield, and I'm going to be presenting, I guess, the first part of our experimental work that we've been going through. So this is the experimental flow sheet, which is quite similar to what David's just covered, where we have first digestate from Cotton Valley going into our HTO unit. This is pressurized with pure oxygen, and then goes through a heating phase to the desired set point temperature. This is held at that temperature for a certain time and then cooled and depressurized. The effluent from this is then fed into a separator, which is a relatively simple gravity-based cloth mesh, and then the solids then can be separated out and dried into a phosphorus-rich ash, and the effluent from this is then fed into the UASB, which is an upflow anaerobic sludge blanket reactor, and that's fed up through the bottom of this, and the methanogens in the sludge blanket then feed on this on the via phase in the effluent and break it down and produce biogas, which is captured at the top of the UASB, and then the effluent from the UASB, the liquid effluent, is then fed into the ammonia stripper, where it operates under vacuum and the effluent's heated to promote the transfer into the gas phase for the ammonia. And this ammonia is then captured with a small amount of water, and return flows taken as well. So this is a visual of what the setup actually looks like at the pilot scale. So we have the HTO unit in the center, which I think, like Trevor talked about, is essentially a large pressure vessel. So this one's 16 liters, and so that's where our digestate and oxygen go into, and then you see the separator is essentially a column which the effluent from the HTO is poured into, and then the liquid phase from that is captured at the bottom, and then can be fed into the UASB, which is on the left. And you can see the column where the effluent is slowly fed up through the sludge blanket, and then the liquid from that is transferred to the stripper, which has a, I'm not sure if you can see it in the picture, but has a packed glass column, which the effluent is slowly trickles down to separate the ammonia out. So for the commissioning runs, we're going to look at the first 10 runs that have been done in order for us to get an idea of and nail down the operating conditions that we want to run for the rest of the trial at. So these first 10 have been focusing on 2 different temperature set points of 220 degrees and 250 degrees, and then various residence times for these as well. The pressure, the base initial pressure has been 50 bar that the reactor has been pressurized to, and stirrer speed has been relatively constant as well. There's been a few changes in initial pressure, stirrer speed, and feed volume, just to explore those and any impacts they may have on the process briefly as well. For the rest of the commissioning runs, this will be built out to comprehensively cover those residence times for those 2 temperature set points, but then also explore the impact of lower feed volume but same pressure, so changing the oxygen excess amount, and also looking at a few kind of baseline runs with glucose, one with raw sewage or raw sludge, and also one with a different pre-treatment on the sludge. So the Cotton Valley sludge is hydrothermally pre-treated, I believe, and then we're looking at one that is enzymatically pre-treated instead to see if that has a difference there. So when characterizing our digestate, this is what the Cotton Valley digestate looks like on the left there. And you can see the COD level for this digestate's around 67, 68 grams per litre, and most of that is made up of particulate COD with a small amount of soluble COD. And that particulate COD is the part that's, I think, like, again, Trevor had said, it's particularly effective at breaking down. And then we have the solids. So we're sitting at around 5.6, 5.7% total solids, with about 60% of those solids being volatiles. Cool. And then this is a visual of, I guess, before and after for the HTO unit itself. So we have digestate on the left, and then we go to the effluent from the HTO reactor. You can see it's separated out quite easily, quite nicely, with the solids sitting at the bottom and then the liquid phase sitting at the top. And this color for the liquid also seems to differ based on our operating conditions. So there'll be runs depending on those operating conditions where it may be darker, where it may be clearer, closer to a water color, more transparent. And then you see the dried ashes as well from the runs. Yeah, that's me. I'll now hand it over to Celeste.
Thank you, Stephen. That's great. So good morning, everyone. I'm Dr. Maria Celeste Gritti, and I'm a researcher here at Cranfield University. And today I will guide you through a brief journey about the preliminary data that we've been gathering through this ongoing commissioning phase. So we've been monitoring key parameters to help us characterize the HTO effluent and also orientate a little bit around the parameters that we want to set for the future runs. In fact, we aim to find a sort of a trade-off between all the different criteria that we use to assess the fitness of the effluent for the downstream applications. And first of all, we've been looking at the levels of COD in the filtered effluent of the HTO. And here you can see the values of the COD concentrations throughout the 10 different runs that we've been doing so far. With the solid bars, you can see the levels of the runs that have been performed at 250 degrees. Overall, the 10 runs, we could see a COD removal ranging between 72 to 87% of the initial COD load, which is great as it shows us the capability for the deconstruction of the technology. And we could see that the levels were ranging between 9 to 19 grams of COD per liter residual in the effluent, which also shows that there is still an organic load that can be a potential. It can be further harnessed downstream through other resource recovery technologies. We observed the lowest level of removal and therefore the highest residual COD for run number 1, which was the one with the mildest conditions at 220 degrees Celsius and with the lowest residence time of just half an hour. However, just based on this data, we cannot draw a direct link between the temperature, the time, and the residual COD. It's something that we might be answering later on with further trials. We also measured the levels of dissolved organic carbon in the effluent, which essentially mirror the COD levels with values ranging between 5 grams DOC per liter to 8.5 grams of dissolved organic carbon per liter in run number 1. So again, the one with the mildest condition. Currently, we're also looking at determining which species contribute to the COD and also quantify their concentration, because this is going to help us to start gathering insights to understand the treatability of the effluent. Based on previous tests and on cytogenics knowledge, we expect most of these to be in form of volatile fatty acids, which is really useful for downstream recovery. And we also going to be test the potential impact of recalcitrant organics that might have been formed during the conversion. So something we'll be looking into. We then move to the next element of interest, which is nitrogen. And here you can see the levels of ammoniacal nitrogen in the effluent after filtration for the 10 runs. And we can see, based on this data, that there is some sort of consistency throughout the runs, with values ranging between 3.9 and 4.5 grams of nitrogen per liter. We cannot draw, again, a direct link between time and temperature, and the ammoniacal nitrogen is something that we will be looking into. And I think it's important to stress how such high values of nitrogen make this stream a very good candidate for resource recovery, especially for the vacuum thermal stripper, as we know that the concentration in the feed of the stripper is potentially also impacting the economic feasibility of the overall unit. So it was great news to determine these values. We then move to the next slides, where we can see the effluent pH for the 10 runs. Overall, most of the runs were ranging between 7.2 and 8 pH, which is another quite remarkable finding, as we know that pH adjustments sometimes can become quite a significant expense for the operational cost. And if we look purely at the pH, we could potentially just feed the HTO effluent straight into the USB without the need to adjust the pH. We are also looking at determining the carbonate alkalinity in the HTO effluent to understand if there is the potential to further increase the pH by stripping CO2, which is particularly interesting for the vacuum thermal stripper for ammonia, as having a higher pH will help us shifting the equilibrium from ammonium to the volatile ammonia. Moving then to the right side of the slides, we look at the effluent solids in the total effluent, so before the filtration. And we see that, first of all, we had a reduction compared to the digest state, which had around 5.7% total solids, while in the HTO effluent, we have around 3.5%. And out of these, about 2/3 are non-volatile. So this links to the next slide, which is all about the dried ashes. First of all, I want to say that we are going to complement all these analyses with determination of carbon, both organic and inorganic, nitrogen and phosphorus in the ashes to fully characterize this product. On the left side, you see an example of the dried ashes. And then on the right side, you see a particle size distribution analysis that we've been performing on the total sample after the HTO process, just to have a representative sample to understand the size of these ashes. And we could see that the majority of them, so 90% of them, are smaller than 33 microns, and only 10% are smaller than 3 microns. So this set the need for a filter mesh size between 1 to 5 microns to maximize the removal of the solids. I also want to stress that these solids are really easily settable. We are going to measure the settling rate, but just by visual observation, we could see that there was a striking difference compared from this solid compared to the digestate solid. So this also opens the possibility potentially for other methods for solid separation, something for the larger scale perhaps. And then I want to give you a bit of a preview of the exciting upcoming months. So we're going to complete the commissioning phase by running few more trials, as Stephen already suggested, where we're going to look at the impact of few more variables, including the sludge type and its pretreatment. In the meantime, we continue the extensive analytical campaign to characterize the HTO effluent with the different runs, and then set some parameters for its operation. Once these are set, we're going to operate it for several months under constant conditions, upon which depend also the feed for the downstream units, so the USB and the stripper. And of course, we're going to be monitoring all the key parameters throughout the flow sheet, because we want to determine the performance of the different technology and also the quality of the product. So ultimately, we're going to close the mass balance and validate the flow sheet mass balance. And finally, we'll also be looking at the treatability requirements for the return flows. And all of this data eventually is going to be used to determine the design parameters for the scaled up treatment train, including the USB and the stripping unit. So thank you for your attention, and I will pass now the lead to Ben.
Thank you, Celeste. I'll take control. Brilliant. All right, yeah. Hi, everyone. So I'm Ben Lickmarty. I'm a process engineer working at Atkins Realis in the bioresources team. So something that we've been working on for a little while is working with everyone in this project to understand how we draw all the threads together that we've seen today. So thinking about deploying hydrothermal oxidation in the water sector. And we've seen the science of it. I've been and seen the lab that Celeste and Stuart will be working in. That's really exciting. And kind of seeing all the threads coming together from being on a page has been really exciting. So I'm going to really think about what this means for us, not just in the UK, but globally, and what the impact could be. So we all understand that there are these huge challenges and forces that are driving us in the water sector towards these kind of technologies. Primarily, I've got these 4 pillars up here that you'll be familiar with. So managing substances of concern, whether it's microplastics or whether it's PFAS or whether it's any other compound that could come out the woodwork in future, is really important to understand that we need to have alternate ways to deal with these beyond just digestion or liming or composting or whatever the base technology we might have is. We also want solutions that, if we're going to deal with that, also help us deal with other problems or unlock other opportunities. So one in the UK that's big at the moment is the Industrial Emissions Directive. That's emissions that can arise from the treatment of digestate or the storage of digestate. Everything we're going to do here will be synergistic with delivering the net zero strategy that certainly we're driving towards for 2030 and beyond. And then, as Will alluded to early on, we really need to move towards a circular economy. And it's projects like this that could help unlock that, because we're looking at producing new resources from sludge and digestate to plug into a circular economy. So the way that we've done this sort of brief exercise is think, okay, we have seen what HTO could look like at a lab scale, and we theorized what it could look like at sort of a demo scale, but what would it look like at full scale? And what impact could it have? So why are we actually driving in this direction? Where does it take us? So if we look at Cotton Valley, which is a site operated by Anglian Water in the UK, it's a water recycling plant serving 260,000 people, and then a sludge treatment center next door producing about 26,000 tons of dry solids per year. And has been alluded to earlier, it's a THP site. So we're dealing with THP digestate. And understanding what would HTO mean on this site helps bring a little bit of color in, basically. So the first thing to understand is, what is the current state? At the moment, then, there's nothing here that will be surprising to anyone who understands how an AD plant works. If we draw the boundary of the digestate that comes out the process, at the moment it is dewatered to produce biosolids, and then those biosolids are put to agriculture for beneficial use. That process also produces concentrated liquors that might be rich in ammonia, so nitrogen, but also carbon, and they go back to the head of the works. Some critical challenges that arise from this kind of really standard formulation here. The digestate, well, that is a potential source of methane emissions or ammonia emissions or other diffuse odorous emissions. And that is a big challenge facing the UK water sector at the moment, and many other places in future potentially, of what do you do with digestate? How do you store it safely? How do you prevent emissions? And where does the line of regulation start and stop? Then you've got the biosoils themselves going to land. Well, we all understand these land bank risks and these substances of emerging concern that could be in them. And there's a uncertainty in the regulatory future here. So like I say, we need alternative options on the table if we're going to help deal with these. And finally, net zero. So that line that's going back to the head of the works contains something like 20 to 30% of the overall nitrogen that's going back into the head of the works. So that means that it's that amount of N2O emission. N2O is a hugely potent greenhouse gas, something like 273 times more potent than CO2 itself. So if we're going to be serious about delivering net zero and then going beyond net zero in the water sector, we need to deal what's happening with the water recycling centre and the N2O emissions that are arising from there. And one of the key ways to do that is tackle this stream, because it's 1% of the total flow but contains 30% of the total nitrogen. So it is almost a no-brainer to deal with, but that is harder than it sounds. But we're going to fold that into this solution. So if we go with where we are at the moment to what a vision could look like for deploying HTO, and there's a lot of to digest here because there's a lot of new boxes. But if we just step through them, you'll see that it's pretty much what Stephen and Celeste have been talking about and what they're developing at that scale. So now you've got digestate, and instead of being dewatered, it goes through a HTO process, and that is breaking down a lot of the organics and solubilizing a lot of the carbon and the nitrogen. Really good question from Ade in the chat about what happens to PFAS and microplastics. So I understand the current evidence is, as Trevor said, is that the microplastics tend to break down. The fate of the PFAS is sort of unknown, but it might be decoupled from the sludge matrix in this, and that is really important for later. Part of the reason we're doing this project is to find these things out, but what comes out of the HTO process will be that sort of discolored liquid that was showed earlier on, with a little bit of ash at the bottom and those really nice vial pictures that we had. So the first step you do is remove the ash. You've got to recover it, maybe a hydrocyclone. And critically, that is now the only solid output leaving this flow sheet. That's how much this is transformative in the way that you're managing biosolids at the moment. That ash will be full of most of the phosphorus that was in the biosolids. And once you remove the solids, you have that sort of yellowy liquid, which is full of dissolved carbon and dissolved ammoniacal ammonia. So the first thing you could do is turn that carbon to work by putting it in an anaerobic bioreactor. It is food, basically, that can be turned into biogas. So why not do that first? Then you're left with a solution which is rich in just ammoniacal nitrogen, and that can go into an ammonia recovery stage. So recovering ammonia as perhaps ammonium sulfate or aqueous ammonia is a really interesting and important resource to have. And again, it will knock on to an emissions impact later on. Now, what's really nice about this ammonia recovery stage, ammonia recovery is sort of a burgeoning opportunity for the water sector. And the question is always, are your liquors concentrated enough? Because the more concentrated they are, the more ammonia they have in terms of grams per litre, the more economic that process will run. Well, because you've done so much organic breakdown ahead of that stage, the liquors are sometimes something like double the concentration you'd expect off a THP plant. So you're really almost in farm AD territory where ammonia strippers make a lot of sense. So that's a really exciting aspect, is actually unlocking, breaking down the nitrogen or releasing it from the sludge as ammonia, and then putting it in a form that you can easily strip off. But what comes out of here? So we've got that blue box in the bottom corner, dilute liquors, which contain some nitrogen still, some carbon, but nowhere near as much as the concentrated liquors on the previous slide. And they all go straight back to the head of the works and cause much less issue than before. And the final box here, which is on the way, is extracting substances of concern. So yeah, playing back to that question, what isn't removed and what has made it all the way through this process? HTO, ash, the bioreactor, the ammonia recovery system. It might be PFAS, it might be PFOS, there might be other chemicals coming out there. The really exciting thing is that we're not trying to solve this in a conventional way. We're not trying to remove those really challenging compounds from a really challenging sludge matrix anymore. We're actually presented them within dilute liquors, which are completely clarified and solid free. So our colleagues in clean water treatment know how to remove PFOS from clean water. And that is the problem we'd be giving them here. There's off-the-shelf technologies, whether it's membrane technologies or activated carbon or foam fractionation, they're established. So you wouldn't be taking an innovation risk here. And what is also really nice is, because you haven't volatilized them or sent them up the flue somewhere, there's also potential for whatever new compounds might be regulated in future to have quite an easy point of removal here. Now we need to test all of this, but that is a really exciting idea. If we talk through some of the benefits of this flow sheet and sort of telegraph them back to those challenges and opportunities then. So the first one is the digestate itself. So you're reducing digestate storage from days down to maybe hours as a buffer, and you're eliminating cake storage and you're no longer putting cake to land. So those challenges around residual emissions sort of go away. In terms of a circular economy, just for the Cotton Valley site, when we crunch the numbers, if you did this at full scale, is a huge amount of sustainable phosphorus could be recovered from that ash, and a huge amount of nitrogen, so sustainable nitrogen recovered from those liquors. That could really play a huge part in promoting that circular economy and understanding how that could fit in, and almost the water sector playing a new role than it has at the moment. From a net zero perspective, there are multiple benefits. So that ash that is leaving site now, that is less than 25% of the total mass leaving site at the moment. So you've got a 75% reduction in the amount of stuff that you're having to take off site. Think of what that means in terms of haulage or scope 3 emissions, or truck movements, or just simply storage. So a huge benefit there. In terms of net zero as well, your anaerobic bioreactor, if you work it through for Cotton Valley, as we have with Daniel, we've thought about something like a 15% increase in biogas recovery for the site on top of what you recover at the THP plant already, because you've further broken things down. And that's sort of a double win, because you're also capturing what would be residual emissions and you're putting them to beneficial use. On that line that goes back to the head of the works then, in terms of net zero, so that far left box, you've got an 80% reduction in N2O potential. So by ripping out all that ammonia and that nitrogen, you've dramatically reduced the emission potential heading back to the works. And the final thing really, in the bottom right-hand corner, the substances of emerging concern, this idea that we could now deploy conventional technologies to remove these substances is a really exciting one. It's something that will be tested at the lab as well. So you can sort of see why we're excited about HTO. It's not just the idea that, you know, it's good science and it would be interesting to test at a lab. This could be completely transformative for the water sector and presents a completely different option to other options that are also on the table for advanced thermal conversion. But I'm a process engineer, so I always think, what's the catch? So as well as crunching the good numbers, I have to crunch the bad. In terms of energy impacts, you've got to really think about what is the difference in terms of energy that this flow sheet would require versus the current state. And you can work it out, or estimate it at least. So the current state, you've just got dewatering. It's just that one box. Whereas if you move on to the right-hand side, you've got this integrated HTO flow sheet with multiple new technologies and processes, all which will have some kind of energy demand. In terms of the integrated HTO flow sheet, there is a clear increase in the amount of power it's going to require. I've worked out, with some uncertainty, something like a 6 times increase in the power demand versus the baseline. And that's largely due to the ammonia stripper itself, but is to do with the HTO and everything else. It's just there's more complexity, there's more things to run, there's more things to pump, and you're working at pressure. There's also heat demand. So that orange bar is this heat demand you didn't have before. Now you need a heat demand because you're ammonia stripping. So understanding how you can meet those is really important. The good news story is that you've got to think of this as a system. So we'd be recovering that biogas within the system too, because we deployed it. So if you imagine taking that biogas and putting it through a CHP at Cotton Valley, well, that heat and power that you could generate on site just using your existing assets would be sufficient to completely negate that new heat demand. So then there's a zero net heat demand for this new flow sheet and take a big chunk out of the power demand. Importantly, the power demand is still a bit higher than the baseline. And if you need some context here, that's something like a 4% increase in Cotton Valley's power demand after you've had this circular solution. But the really exciting thing is that you're also reducing power demand elsewhere in the flow sheet. So if you widen your energy balance to think about the water recycling center next door, it has to treat a lot less ammonia and a lot less carbon. Not only that, you've eliminated your challenges around biosoils to land, your emerging contaminants challenge have been knocked out before they head back to the works, and you've got these new resources to play with in a circular economy. Now, all these numbers need to be checked and validated, but that's part of the reason why the science that's going on at the moment and that those test runs are happening at Cranfield are really exciting, because they can feed into these numbers. And at the end of this project, we'll have a much better projection, and we'll be continuing to be increasing accuracy the whole time. So I'm now going to hand over back to Leah, I think. Thank you very much.
Thanks so much, Ben, and thank you so much to the team so far for the fantastic presentation. We hope that the audience has found it valuable so far and informative. Some really exciting work going on, which is great to see. So we're going to take a very quick break. You don't need to do anything. You already have your cameras and mics off, so no need to leave the call or anything like that. Just pop and do what you need to do. We will be putting the poll into the chat that I mentioned at the beginning of the call today. If you could please just take a moment to fill that in if you do need to jump off, or you can fill it in at the end again when we do share that. For those who are curious, this presentation is recorded and will be put on the Spring platform after the showcase today, alongside a written version of the case study too. So the time is 11:08. We're going to do just a quick 5-minute break. So as we'll come back about 11:13 to hear a deeper dive into the lessons learned from this project before we then go into our Q&A. So if you do have any questions for the presenters, do keep popping those in the chat throughout the next half an hour or so. Thanks everyone. Enjoy. Okay, welcome back everybody. So we'll now be restarting the presentation. So we'll be going into a discussion about the lessons learned from this project, a bit of a deep dive into the challenges, how they were overcome. I believe that involves all of our presenters. So if all of our presenters could show their lovely faces, please put your cameras and mics back on. And we don't have a slide for this section or for the Q&A, so I'm actually going to stop sharing so that you can see our lovely presenters a little bit better. Perfect. So David, feel free to take it away when you're ready.
Thanks, Leah. Hi again, everyone. So welcome back. So we've got a number of lessons learned so far. As I said earlier, we're midway through the project. We're in the early stages of phase 2, which is the experimental work. But we do have some lessons learned. And the first that I'm going to talk around is around the value complexity, the value case complexity for HTO, but believe this also applies to other advanced thermal conversion projects. So circular economy leads to us needing to consider more factors than a normal business case. So in the case of HTO, there are various byproducts that we can produce from sludge, and this means that there are potential new revenue streams as well. But these are subject to market forces. They're also subject to quality control requirements. So these market forces and other factors, they become important in the value proposition for HTO, and actually they cause some uncertainty at this stage. We need to be sure that whatever alternative approach we're taking to sludge to land doesn't undervalue biosolids, but also achieves those outcomes that we want in terms of managing substances of concern, and net zero and resource recovery. So if we're using sludge to land as our sort of our benchmark, where the phosphorus of content determines the cost of bioresources, we have that as our benchmark, but we need to look at what the value of these new products that we're potentially bringing to market are, and one of those things is around the robustness of the value chain, which at this stage, as I said, there's some uncertainties around. So and part of one of the ways that uncertainty will be removed is having a developed regulatory framework for the products. So one of the current steps and the next steps that we're working with the EA, we're looking to work with the EA on end of waste status for the phosphorus, ammonia, and carbon-based products. So it's a lesson learned, but it's the complexity really around when we're evaluating ATC processes, that regulatory framework, it isn't quite there yet. So we need to meet that some way, and I think that's where the collaboration with regulators, the collaboration like on these type of meetings where we can talk with others, and invite those comments and different viewpoints is important, which we are doing with potential off-takers at the moment. So that's one of the lessons learned. A second one, I'm going to hand over to Bruce Jefferson and Steve Riches. So Bruce from Cranfield and Steve from Atkins, just to talk a bit about planning and the timing of the projects that we've experienced in the HTO All Streams HTO project. So over to you, Steve and Bruce.
Okay. Hi everybody. As David said, I'm Steve Riches, Associate Director at Atkins Realis. So I've been helping doing the sort of program management of the work so far. I guess for me, the sort of lessons learned, I guess, is around sort of commencement and startup. I think it's probably easy to get I guess all excited when the funding comes through and keen to get going, but there are obviously those various sorts of contractual complexities and bringing the sort of consortium together to get agreements signed in place. We then have to navigate the procurement of the equipment. Again, that did take a little longer than we anticipated. However, there was some good reason for that, as has been presented. The process is in a laboratory setting. It involves pressure, pure oxygen, etc. So it's making sure that we did that with safety first, really, in mind. Making sure that what we delivered was safe and easy to operate. So we very much worked with Bruce and team before Celeste and Stephen came on board to make sure we selected the best equipment for the job. So that did involve quite extensive assessment of the supply chain, interviews with the reactor providers before making a final decision, and HAZOPs and pre-commissioning checks before we went live with the project. And I guess out of that HAZOP, we did pick up a number of minor modifications that we needed to make to the project before the plant went live. So I guess that's my reflections really, is to make sure that all of those I guess which could be considered perhaps the less exciting parts of the project in terms of planning and programming and getting everything lined up in a row before you sort of commit to spending the money essentially to get the plant there are fully aligned and in place. Bruce, do you want to add anything to that? Sure, he's there. It's quiet. If he's not there, I'll hand back to you, David.
Yeah, no problem. Thank you. Thanks for that, Steve. So lessons learned still. A third one is really a broader lesson around how this type of project and the approach that Ofwat are taking allows the water sector to be brave. It does come with innovation, comes with inherent risk, and as you've seen from the work we're doing, there are uncertainties. That's why we do innovation. And you know, I'm going to hand over to Ben actually just to talk around that a little bit and how we've experienced that and also how we've managed that through this project. Thanks, Ben.
Thanks, David. So yeah, it will be unfamiliar to no one, the idea that the water sector has to be conservative with how it spends its money because we're spending customer money. So the idea that you could have innovation funds like this really unlock the possibility to do something different or to try something radical. And there's already been really good engagement in the chat about this just being something that wasn't necessarily on the table before people have heard us talking about it as an idea. So there's something a little bit left field about it, and that's what's fascinating. So I think the idea that the truth is that we don't know how those blocks are going to be arranged on the page yet. So we talk with certainty, but actually we don't know if the ammonia stripper comes before the anaerobic bioreactor, or what the level of PFAS destruction will be, or what level of microplastic destruction will be. But we have a very good idea, and we have a principle that we're working towards. And so being able to have the time and the space for Celeste and Stuart to do their thing and work in the lab and build what they're building is fantastic. And then we can all benefit from that data and turning it around different ways. So I think just the freedom to operate a little bit and go into an area where, yes, we don't necessarily know the answers going in, has been really exciting. And that is also the best thing. I think one of the best things about this project is the level of dissemination with other projects. So there are a whole load of range of projects working on advanced thermal conversion in the UK water sector at the moment. And everybody through the likes of David, they're all talking to each other and sharing it with each other. So there is not a one-horse race. And so the idea that there is availability to try these different options and then discuss them and see what works and learn from each other itself has been fantastic. So I guess it's just that opportunity that's been open to us.
Great, thanks, Ben. Yeah, and just to add to that, you know, I work in the research and innovation team in Anglian, and you know, the approach that Ofwat have taken, and then what it's allowed us to do in this project is to take an open innovation approach. So we're learning so much, and we're able to share that. But it provides Anglian as a company confidence to move forward with this approach, working in partnership with you know, our historical partners, Cranfield, with Atkins, and then developing relationships with Cetogenics as well. So it's a good model for I think what we're aiming for. Bruce, notice you're back. We were talking there a little bit. Steve was talking around the project timing and some of the sort of expectations we had early on. I didn't know if you wanted to add a bit on that from your experience from a Cranfield perspective.
Yeah, just very briefly, I think we just need to be a bit more mindful of how challenging some of those early stages can be and the time it can take up. Because otherwise we get behind the curve almost straight away, and it generates a more negative environment to actually move forward in. So if there's a learning, it's trying to just provide a little bit more of a cushion so it can all feel much more positive from the very beginning. That would be my observation.
No, yeah, thanks for that. Great. Yeah, and always, I know from your perspective, it's you know, we want to get the right outcomes in terms of the science, and that needs to be a priority. And yeah, so sometimes when we're building and we're doing the HAZOPs and doing the health and safety stuff, we can lose sight of that, can't we? So thanks, Bruce. So another lesson learned, I'm going to hand over to Daniel on this one, which is around working across sort of international. This is quite an international project, working across time zones, and but also, yeah, some pros and cons of that really. So we've had some great developments with knowledge sharing with Cetogenics. So I'll hand over to Daniel and Trevor on this. Thanks, Daniel.
Yeah, thanks, David. And yeah, so we're certainly international team, and here we are in New Zealand, which is almost perfectly misaligned with the UK in terms of any time that you can interact. And so someone is always up late at night when meetings are held, and so it comes with some challenges. And what we've, I think, a big thing that we've learned is that nothing beats face to face, and so committing to being over in the UK has been a big part of Cetogenics' journey in this program, and it's a long way to travel, but it's fully worth it. And so I just returned a few days ago from a couple of weeks in the UK, and it just nothing beats being together face to face and talking through challenges and seeing how the work is really going. And I think a really great part of that has been the literal transfer of personnel, if you like. So Stephen Stewart is a proud Kiwi, and he's sitting in the UK working in the Cranfield Labs. And so we had him as a student intern a couple of years ago at Cetogenics, and as things moved and transpired, he moved over to the UK to take up a master's program there. And I think that's just been super valuable for all parties. And so some things to reflect on there about presence.
I'll only add one quick point, of course. The other challenge of being literally halfway around the world is we obviously, it's very difficult to process UK samples. We can't really send UK biosolid samples to the other side of the world and run them in our prototype. So we've had to be somewhat doing our work by proxy in terms of our prototyping and using New Zealand-based feedstocks, which is a perfectly reasonable fit proxy, but not ideal, because there are significant differences in some of the operations. That's why we're hoping, as we go forward with the project, there'll be an opportunity for our sort of scale-up technology, then our prototypes to then be located in the UK. We can overcome those barriers to testing, in sort of the continuous process that our prototypes are operating in now. So we look forward to that.
Thanks, Trevor. Thanks, Daniel. So, yeah, that's the main lessons learned from the project so far. We will have more, and as we move to the end of the project, early to mid next year, we're planning a second showcase. So there'll be more to present and a lot more data. So, but for now, I'm going to hand back over to Leah for the Q&A.
Great, thanks so much, everybody. It's really great to see such a open and collaborative discussion happening around the learnings from this project. So thank you for that. Great, so diving straight into the Q&A, and do keep putting your questions in for the audience if you have any that pop up through this. We will try and get to them all before the end of the session today. But to start things off, and we have sent a response to this in the chat, but it might be nice just to kind of loop back and give it a good discussion now. Is that Cetogenics said that HTO promotes deconstruction instead of destruction of the components present in a digest state. In relation to PFAS and microplastics, does your HTO system destroy or just transfer those contaminants to the HTO products? Thanks.
Yeah, so I answered this in the chat, but basically, yeah, the microplastics and bulk plastics, because often there are bulk plastics, also get broken down basically into VFAs or organic acids, and then they are subsequently fermented just as the others are from the organic waste. So in that sense, they contribute to the value add of the carbon, even though technically not biogenic, but they certainly get broken down and destroyed. Also answered on PFAS, and I know Ben touched on this a little bit, that we don't have data yet on PFAS, but we are either destroying them or we're eliminating the matrix to allow them to be recovered and destroyed. So we hope that's a win-win one way or the other with respect to PFAS, but we're looking forward to the opportunity to test the samples and look at the PFAS data.
Perfect.
Perhaps I can just add a little bit around PFAS. So one of the key challenges with PFAS is particle and colloidal association, and we will have broken that linkage here with HTO. So where in sludge liquor returns, which will still contain a significant proportion of PFAS, they've still got that challenge. We won't have that. The other challenge that you tend to get for PFAS removal is about the background matrix and the amount of alternative hydrophobic material that you've got to remove. Now, we will have changed that, and we will be modelling the organics to understand that, so that we can understand how much we can exploit the hydrophobicity difference of PFAS to the other organics. And as Ben said, this moves us towards the type of technologies that are used for drinking water, although I just need a slight amendment in that the background matrix is still going to be more polluted than we would typically see in a drinking water source. So we've got to understand the adaptation of those technologies to these liquors. But it's the only opportunity within biosolids management where you could start to think about applying those technologies with any sort of sense, really. All the others would be very challenging because the remaining nature of the liquids that they're having to process. All right, thank you.
Great, thanks so much, Bruce, really insightful. And the next question is from Jason. Again, we have sent a couple of responses to these questions, a few of these questions in the chat, but just giving the presenters a chance to add on to any thoughts that they've got. So from Jason, over what duration and range of operating conditions will the trial be run, e.g. stability over weeks and months and not just short batches?
Perhaps I can take this one. So fundamentally, the trial is using a batch reactor because at the scale we're trying to do the operation, it's the only sensible way to deliver HTO. But what we're trying to do is we won't be varying conditions once we start the trial. So we will use exactly the same temperature and time throughout the trial, which will last somewhere between 6 and 8 months, so that we can get the equivalent of looking at the variability that you would see during a continuous plant operation. It's the best way to convert batch to continuous data. And so it will deliver the learning because we'll be monitoring every batch. So we process a batch of sludge a day, and then we will be doing 4 batches a week, so that we can look at how much batch to batch we vary the outcomes, and that will give us that translation to what variation might occur in a full-scale plant. So we've chosen to not look at multiple sludges or change conditions very much, apart from during commissioning, so that we can get that quantity of data to be very robust in the mass and recovery balances that we will generate, and understand the resilience and robustness of both HTO and the downstream technologies in delivering this. And just to add on that, we're also from that able to generate the design variables that link to the stripper, to the UASB, that would then translate to full-scale operation. So we will have the design detail needed to translate it to the site.
Great, thanks so much.
Just to add on to the end of what Bruce has said, it's the goal of the next project that we would essentially be entering into field trials, continuous processing in the field on a site, and that's so the questions asked there about operating that's what it's going to be all about. How long can we run for in a continuous fashion? So that will be a primary focus of that next stage.
Great, thank you. And David, at some point in your presentation, you mentioned 2 months. Was this for the experiment or the application of a cetogenic system? And what is the expected runtime and shutdown required for maintenance when operating these systems at a relevant scale?
Sorry, yes, that maybe I may have said the 2 months was just referring to since commissioning, and then we're currently in an optimization stage. So we've been running for 2 months. As Bruce said, the experimental work we have in total is 9 months. So we've got another 7 to 8 months to run to actually do the tests. So
great, thank you. And another one from Jason is the issue we're dealing with CECs in a separate, albeit simplified stream, then that it throws out the energy emissions balance and therefore impacts on benefits of initial HTO treatment? I think that's one for you, Ben.
Yeah, and it's a really good question, Jason. I think we've always got to look at the whole system. A lot of this is just with learning, basically, until we create those liquors and start testing them. And I see you've put also another good comment about things like foam fractionation. So understanding what approach we need to take to remove those will allow us to start developing that holistic balance. So basically, my kind of ambition is that as we keep going, those pictures and those really simple flow sheets I populated start to get more and more complex and closer to reality as we bolt on and get more and more certainty. But yeah, I think watch this space basically, and the next showcase, hopefully we'll be able to tell you.
Perfect. Thank you, Ben.
Sorry, can I just add to that? I think we mustn't forget that the PFAS and the energy and the carbon associated with PFAS will apply to all of the possible answers that will go forward. So actually the question is this more or less energy efficient than if we've got to get sludge to land or using a different ATC? I think we have to accept there's going to be an increase in energy usage linked to chemicals of emerging concern. It's just not going to be avoidable if we're going to remove them. So then it's about the relative benefit of one over the other. And just quickly on the foam fractionation. Foam fractionation is indeed one of the technologies we're considering for PFAS removal. At Cranfield here, we do a lot of the work on PFAS in drinking water, which includes PFAS of the concentrate. So we are going to be translating that learning into these liquids so that we don't double do something. Okay.
Perfect. Thanks so much. Great. So next question is from Gabrielle, who first of all wanted to say thank you for showcasing such an innovative solution, which is great to see. And that recently we've noticed that a few EU countries are actually undermining the benefits of the Green Deal and the goal of net zero emissions. Do you have any concerns about the current political situation in Europe, particularly regarding funding cuts for circular economy projects?
The very short answer is we're always worried about those sorts of things, but it depends how they pan out. And we must recognise here the great opportunity that Ofwat Fund has provided as an alternative source to deliver some of these great innovations. So it's decoupled our reliance on EU funding sources to deliver some of those things. I mean, I think our impression at this stage is that there's still plenty of activity going on across Europe, and I think maybe it's a bit about reframing rather than just all or nothing. But I would say that's not new. You know, I've been at Cranfield 28 years, and I'd say that issue of reframing to adjust to how things change is part of the job of research. So I think it's not complete decoupling. It's just a bit of adjustment. I think the same goals can still be delivered, just within a perhaps revised narrative.
Right, thank you.
If I can add to that a bit as well, please, Leah. There are also other entities in Europe which I know are doing some really great work on this. So I know lots of Dutch water companies in particular have invested quite heavily in circular economy solutions, and they can provide a really useful link back to us. And even if it's not central EU funded, there's still plenty of international interest in this area. And on the water company level, even there's some really great work going on. So, you know, treating Europe as a monolith is perhaps a little bit short-sighted, I think, in a way, because there are some fantastic other alternative options there as well.
Yeah, and I'll probably add to that as well. I recently presented on hydrothermal treatment overseas in Canada a couple of weeks ago, and there is genuine interest, I think, in how these technologies can help decarbonise, and I'd echo what Bruce says. Really, I think it's a little bit reframing, but I think the underlining interest is still there, and there was certainly a lot of interest in this particular technology, in the role it can play in supporting companies meet their sort of green/net zero ambitions, particularly around the point I found last week when I was when I presented, was around the that ability to, if you like, reduce the overall sort of system impact emissions when you look at the NOx and the liquors that are avoided being returned by going with this type of approach. So like Bruce, I think it's more of a reframing. I think the need is probably still there and recognised, and yes, we might have to adjust to navigate through, but I think its underlying need is there.
Great, thank you, Stephen. Did any other of our presenters have any thoughts they'd like to share on that, or before we move on to the next question? No? Okay, thank you all. Great, so the next question is, if using CHP, how much of the additional energy / heat demand could be met from the plus 15% biogas yield?
I can pick this one up. Yeah, I think this is a really important point. So understanding that we're going to both be increasing the amount of energy that we need to use, and as Bruce said, that baseline might go up anyway, but we're also generating energy. Now, if we just understand that if we did the simplest thing and burned the biogas in the CHP, we've run the numbers, we know the flows, we know the carbon, we know the nitrogen, it looks like the heat demand could be totally satisfied by the heat that we kick out the back end of the CHP. And most of that heat demand is about the ammonia stripping process, which needs to operate at something like 70 to 85 degrees. So it's in raising the temperature, because the HTO unit itself could be run autothermally. So if you think the biggest heat sink is the ammonia stripper, and you could cover that with the CHP heat, you could also take a very big knockout, about 2/3 out of the additional power demand, using the new power generated by the CHP. However, what we also kind of need to think about is the world we're going into might not use CHPs. We might be upgrading our biogas or something else. But understanding that is the energy coming out is almost enough to cover the new energy demands is really important. Another factor is the point that the ammonia stripper is actually a large user of electricity in terms of power and in heat. The ammonia stripper itself actually emerges quite highly on it, because it is quite a big stream to put through one of those, which is why part of the project is developing a novel ammonia stripper, and Celeste has been building it and will be running it, which is aimed at reducing the energy demand of that unit, because that is the biggest potential win. And that innovation itself could have, translating benefits across the sector. But let's not go into that now, we're right at the end. But very exciting anyway. I'm going to hand back over anyway.
Thanks, Ben. That's great. Next question from Jane. Would the project team please be able to estimate the time needed to get to TRL 9, please? Would it be about 5 to 10 years or more or less?
Thanks, Jane. I can take this one. And I'll hand over to Trevor as well, who's so yeah, as you've seen, we're looking at a system. So this is a system for hydrothermal oxidation along with downstream recovery. So there's a number of steps we need to go through, and at the moment we're in the process of putting together a Ofwat Innovation Fund bid for round 6, which is going to be a larger project, a transform bid. And the aim of that project is to get to TRL 8. So I would say, in short, the timing, given that we'd be looking to get to TRL 8 within 3 years, then I'd say TRL 9 would be realistic within 5 years. There are questions to answer, obviously, and there's uncertainties in that, but that's where we are in terms of the whole system. So we need to remember there's continuous HTO, then there's the vacuum ammonia strip, and there's the recovery steps. So, but yeah, hand over to Trevor as well to talk around that as well.
I was hopeful you'd answer that one, David, because I think it is about the system, but I think from a cetogenics perspective, the core platform, the CETOburst system, I guess we're also pursuing that in parallel in other systems that don't require that systems approach, such as agriculture and so forth. So I guess we would hope that the CETOburst core technology, the modular system, would be at TRL9 probably within 24 to 36 months, but that doesn't account for the other elements that you're talking about. And that's probably a naive startup founder CEO's perspective as well.
Great, thank you so much. And question from Richard for David. You highlighted the possibility of using pea ash in cement production. Any ideas of volumes and how relevant this would be to decarbonising cement production?
Thanks, Richard. Yeah, so in terms of volumes, we can estimate just really based on the TDS, the total dry solids going in, and then the organics destruction. So we could estimate that. As Ben said, we're looking at reducing the amount of solids taken away from site by 75%, but we expect that to be more a bigger solids reduction. So we could estimate, based on our current volumes of cake, we could estimate that. In terms of decarbonising cement production, there's a broader piece of work here to do around end of waste and around the suitability of that material, and if that is the most valuable route actually as well, you know. And that piece of work around the product and the value chains is part of the transform bid, which will be working with cement producers who are included in that bid. So we, hopefully we'll be answering that question through that project.
Great, thank you so much. A couple of questions from Peter. Do you have already data that shows the digestibility of the HTO effluent and the increase in biogas?
Well, from a cetogenic, I answered this, but from a cetogenics perspective, yes, we've got lots and lots of data, arguably over 20 years of data, but it's all New Zealand-based feedstocks and circumstances, and so it doesn't necessarily the feedstocks that are being addressed in this project. So that's why it's important that this work be also done at Cranfield using the new system so that we can calibrate against that. So I think you made a note, Leah, we're happy to share some of that data with people online if they wish to see it. But again, with the caveat, it's not UK based and therefore caveat of source and approach.
Perfect.
And if I can perhaps just add, so yeah, Peter, we're just doing it right now, I would say. So it's as part of the commissioning run. I think the evidence today through our analysis is that we think, if anything, it's going to be a bit better than the data Trevor's going to share. In fact, it looks a bit richer in VFAs than has previously been done, but we've got to verify all of that before we start getting too overly excited. But the promise at the moment is that it's looking better than we might have initially expected. So, but we've got to verify, and we'll be verifying. We'll know within the next month, I would say, roughly about where we sit with that.
Perfect, thanks so much. And would increasing the percentage DS input from 6%, say, to 8 or 10% be possible? And would that increase the efficiency of the HTO process?
So I can
Daniel.
So in theory, yes. In practical application, that's the question, actually, because as you work with thicker and thicker solids, the practicalities of moving those into and through the system become challenging, and there's some intricacies within the process around things like getting enough oxygen into the system, etc. That there may provide an upper limit to the solids content. But in principle basis, the higher the concentration, the better. So it turns into a question of practicality and engineering.
Yeah, I was going to just add to that. I guess, as Ben outlined in his answer, a lot of the energy input is actually in the vacuum ammonia stripper, isn't it? Not necessarily the HTO unit. And I guess the other thing with here, particularly with the Cotton Valley example, it follows thermal hydrolysis and digestion, so that sludges naturally in that 5 to 6% dry solids window, which eliminates that need for dewatering. I think if we were trying to push to say 10% or 12%, whatever the number may be, you're then bringing back in that liquor stream that you've now eliminated essentially. So it needs to be looked at a system-wide balance. And whilst I've probably got the floor, I'll probably take. There was another question on there about can you use other feedstocks, so a non-digested feedstock. Again, yes, you can. You can use other feedstocks, but I think when you look at it as a system and you consider the sort of asset base that's typically gone in the UK in the last 10, 15 years with sort of centralized sludge treatment centres, a lot of investment that's gone into advanced anaerobic digestion and thermal hydrolysis in particular. You're not likely anytime soon to switch those assets off. And when you say you look at it as an energy balance across the whole system, I suspect there are advantages to doing as we suggest at Cotton Valley and following that approach.
Great.
Just add on to that, I think HTO lends itself best to poorly digestible or recalcitrant organic materials, primarily because if they're readily digestible, then nature and microbiology is a pretty efficient way of breaking them down through anaerobic digestion. So yes, we certainly at Cetogenics have some clients who want to avoid anaerobic digestion up front, mostly for other reasons such as land availability and otherwise, but I think we're sacrificing some of the carbon content, energy content by breaking it down through hydrothermal oxidation. So it's always good in many cases to use the efficiency of nature and microbiology to do readily digestible material.
Great, thank you so much. And are you able at all to, so David, I think you spoke a little bit on in the learning section about risk kind of being an inherent part of innovation. Is there any risks that you can foresee for the work associated with scaling up from a small demonstration plant to full commercial deployment?
Yes, there are. Yeah, there are risks. There's certainly, what we're trying to establish in this project is that process stream that across those different steps, that as Celeste presented the pH data, that's really important. That we make, if we can get as close to neutral as 7 as possible, then we're not having to add chemical, and all those processes will work without chemical addition. And be more efficient. So that's a risk that within this project, but then further forward it's probably more about the system integration. So once we've demonstrated that those process blocks work well together, then it's saying, okay, can we now have this on a live site, and for all of those different streams to be to function as they did in the lab, sort of thing. That's the nature of innovation, and in this perhaps it's slightly more complex because we're looking at a system. But I think in that way, that this project is also quite unique, is that we are looking at truly the end-to-end process, not just looking at HTO. We're looking at what that enables and making sure as much as possible that we're mitigating risks before we go to the next scale. So yeah, there are risks. I think we understand most of them, and we're trying to foresee that and sort of design with that in mind.
Great, thank you so much. I think that about brings us to the end of the session today. So just thank you so much again to all of our presenters for all the hard work that went into the presentation today, and for sharing so openly and honestly about the learnings from the project too. Thank you all again to the audience for joining us today as well, for taking 2 hours out of your day to do so, and we really hope you found some valuable learnings to take away with you and back to your own organisations. If you have, please do let us know in our poll. As we say, answering our poll is the most impactful way that you can help us make sure these events are providing value to you. and your organisation, as well as the wider sector, and that these showcases are completing the mission of supporting faster paced adoption of solutions. Your insights not only help us understand the actions you plan to take on the knowledge shared today, but if there's anything more that we could have done or shared to ensure a successful transfer of the key insights from this project. So please do, before you go, give us a moment to fill in that survey. The showcase recording, as I say, alongside the written case study, will be uploaded to the Spring platform, hopefully within a week or two after the event today. So anybody who wants to see that case study, let me know in the feedback poll too, and I can make sure that I send it to you once that's through. I think that brings us to the end of the session today. So just again, thank you to everybody involved, and I hope you have a lovely rest of your day. Thanks, everyone.
Thank you.